digging in to DNS. The domain name system, we've looked at it together in a previous nugget, and we understand how it works. We have a name of a server that we want to get to. We send out this request, and magically comes back to us the IP address we can use to reach it. It's almost too good to be true. It's a fantastic system, and that's why it's called domain name system, because it's not just one server, it's a collection of servers working together. And in this nugget, you and I, we get to go behind the scenes to take a look at exactly how DNS really works and some tools that you can use to help troubleshoot it or at least verify that it's working correctly. Let's jump in. One of the tools that I often take for granted is DNS, the domain name system. For example, this little PC, which is this PC on our network right here, if we want to go out to the web, we just open up a browser and we go for it. We go to www.cisco.com, or we could go to www.juniper.net, and it just takes us there. We don't even have to worry about IP addresses, but in the background, there's an amazing system of domain name servers that are all allowing us to resolve names like juniper.net into an IP address. So DNS is appropriately named domain name system because it's not just one device, it's a system of devices that are providing this functionality. So let me share with you how it works. On our computer right here, we've been assigned an IP address that we can use. We've been assigned an IP address to use as a default gateway. For example, maybe we're .51 on this network and the router's .1. And we've also been assigned a DNS server to use. And they give us the IP address. So for example, maybe the IP address of the DNS server is 8888. That happens to be currently a public DNS server provided by Google. So the reason that we're given the IP address of a DNS server is because if they gave us the name of a DNS server, we wouldn't know how to resolve that to an IP address. So we're given an IP address of a DNS server so we can resolve it. And a DNS query is so simple. Let's actually track one. So let's go ahead and bring over my PC again. And on the PC, let's just start up a protocol analyzer, and I'm going to sniff the wire. And we can sniff the wire virtually anywhere we want. We've been traditionally sniffing it right here, but we could sniff it on this network segment or this network segment. The only difference for a DNS request from this PC going out to the internet is that if we sniff it right here on this network segment, we'll see the layer 2 source addresses being the router, this router, and the destination layer 2 address being this router. But everything at layer 3 and higher, the source IP address and the destination IP address, that'll all be the same. So let's go ahead and sniff right where we have been in the past, right there. So I'll just open that up, start the capturing. Capturing's going, and let's go to Sun. Oh, I guess it's Oracle now, isn't it? Go to oracle.com. So there's Oracle's website. I think I pressed enter. It's thinking about it. Okay, there we go. So there's Oracle's website. And if we look at the protocol analysis and focus on the DNS, we can remind ourselves not only of how it works, but we can also remind ourselves about the well-known port associated with DNS. So we'll bring in our protocol analyzer, and here it is. Put it right there on top. And here's our request. So my address on my PC is 10.1.0.51. These numbers on the far left are the sequence numbers of the packets that were captured. And the destination was 8888. Now, why did we use 8888? Let me show you what I did. So I went to the properties of my interface, and I told it that I want to not use a DHCP address. I want to use a static address. So I hard-coded my IP address. I also hard-coded the DNS server that I want to use. So because of that, if we look at this trace back here, it's going to show us that the DNS Destination Address for the request was from my PC. If we look at the layer 3 header right here, so it's from my address 10.1.0.51 to the destination 8888. And if we looked at the layer 2 information, it would show us that it's the frame, the layer 2 addresses between me and my default gateway. Again, the layer 2 addresses are going to change every hop of the way, but the IP packet, that source and destination IP address, will stay the same from the source all the way to the destination. So we made a request, and then we had a response that came in, and the response, I'm looking at this right here, Kazaa, which is a little bothersome. Anyway, we'll take a look at it in a moment. So I got the response back in, and the response said in the DNS response, it said the answer to your question, my friend, is oracle.com, and it says here's the A record, and the address is 23.44.65.55. So now that I'm going to that IP address, this is interesting. Oh, it says Kazaa because of the port. All right, I'm okay now. So it's showing us that I'm going from my PC to that device. Now let me show you why I just freaked out a little bit. Kazaa is an example of a peer-to-peer networking protocol. And what happened is my protocol analyzer looked at my source port that I'm using for this conversation right here, and it just happened to match one that Kazaa uses. So my protocol analyzer said, oh, you must have Kazaa. It's not Kazaa. It just happens to be that's the random port that I sourced going to the well-known port of 80 for this individual session. So here's our three-way handshake. That's my sequence request. That's the acknowledgement and the sequencing of the server and at Oracle. And then there's a final acknowledgement by me. And then we have the rest of our HTTP conversation right here with layers 5, the application layer, layers 4, 3, 2, and then the physical layer as well. So DNS, what does it do for a living? It allows you to resolve names to IP addresses, and how exactly it works is a little bit more involved than just making a simple request. So let's get out some pen and paper and talk about this together, about the details of what's really going on behind the scenes. 8.8.8.8, and that's Google's public DNS server. So that device right there is called a resolving name server. And I'll call it a DNS server. You know why it's called a resolving DNS server? Because if I ask a question saying, hey, what's the IP address of oracle.com, it can resolve that to an IP address and give me an answer. Well, let's say the internet just turned on. Everything just booted up, including this DNS server at Google. I'll tell you what, this DNS server at Google doesn't know all the IP addresses of every device on the internet. There's, millions and millions and millions and millions of devices on the internet that have IP addresses, and this one server from Google doesn't know them all. So here's what happens if the internet was just turned on, the whole thing was rebooted, and my client makes a request. The request would go out to my resolving DNS server, and I'd ask, hey, I'm looking for the IP address of Oracle, in my example, .com. Now, because this DNS server was just brought up, it doesn't know the name server or the IP address of oracle.com. So what it will do, it will actually go up to what's called a root level server. And we can make this like an inverted tree. So there's the root, and there's a bunch of servers there. And these root level servers, they're like the wise masters that know everything, or they know where to send you. So the DNS server here asks a root server, and this guy has maybe 24 or 30, I don't know the exact number, it could change, of root servers available to ask. So he goes to a root server and says, oh, I have a client. It's a really good story. He wants to know where oracle.com is. I don't know where that is. I wonder if you could help me. Well, the reply back from the root server is, you know what? I don't know. I'm not the authoritative DNS server that houses that IP address. I don't know exactly, but what I can tell you is I can tell you where the .com servers are. So the reply back is going to basically tell us to go to a bunch of servers, I'll draw them right here, that are responsible for the .com. And these are called top level domain. DNS servers. So it goes like this. We have some servers up here at the root. The root know where the .com servers are. Guess what they also know? If we want to go to anything that ends with .net, the root servers know where they are. And .biz and everything else. So in this process, it started off with the client who made the request to the resolving DNS server who didn't know. The resolving server went to a root server. The root server said, I don't know, but here's the correct .com. And now the .com servers, when we make the next request, they're in different color. So our next request goes up to a .com server saying, hey, I need to know the IP address of oracle.com. These guys can reply back saying, you know what? I don't know exactly about oracle.com, the specific web server. However, I can give you the IP address of the authoritative server, and that's the next level here. So an authoritative server, authoritative, the authoritative server, we're going to have one for, what was the company? Oracle. And we'd have another authoritative server or more for example, Cisco. And under Juniper, they would have, under .net, there would be one for Juniper. And so as we get redirected, this resolving DNS server went to the root to find out where the .com were, who referred them to the authoritative DNS server for Oracle. And that DNS server for Oracle, hopefully, could go ahead and reply with the answer. And that's how the whole system works. I, for one, take DNS for granted. We send out a request, it gives us a name, and I'm just grateful that it's all working. But behind the scenes, there's a lot of moving parts. Now, in order to avoid that again, this resolving DNS server is going to put the answer for that. And what is the answer? The answer is the IP address for Oracle was, I'm going to write it right here, 23.44.65.55. So that's the answer we got back if we had to do that whole questionnaire process. So we're going to put that information in memory on the resolving DNS server. And that memory they call a cache. C-A-C-H-E. So it goes into cache, a memory space on that resolving DNS server. You know why? So the next time somebody says, hey, can you tell me where oracle.com is? The resolving DNS server can look in its cache and say, oh, you know what? I know exactly where it is. It's at 23.44.66.65.55, and feed that answer back. So initially, we have to do a bunch of queries to resolve names to IP addresses. But after one query, these devices can cache that. So when we really go to a website, such as www.cbtnuggets.com, I want you to think of this string as the root being right here. So who knows where the .com are? It's the root name servers. So they know how to get to the .com servers. And the .com, we have the top level domain servers, and they are responsible for, there's a whole bunch of them for .com, there's a whole bunch for .net, there's a whole bunch for .biz and .ws and everything else. And those top level domain servers, they know how to reach the authoritative name servers, also called DNS servers. An authoritative DNS server is where an administrator actually went in and configured the IP address associated with the name on a server. And if an authoritative server is somebody who has it configured, a non-authoritative server would be somebody who had that information cached. So if we're getting information from a non-authoritative server, it's still probably accurate. It just means it didn't come from the horse's mouth. It was cached somewhere along the path. So if we go back and look at our protocol analysis here, I want to point out a couple other things about DNS. So we're describing DNS concepts and components. If we dig into the DNS itself, what layer 4 protocol are we using for DNS? Are we using TCP or UDP? And if we look at this, the destination port, or the layer 4 protocol is UDP. So if we make a DNS request, there's no tracking, meaning there's no tracking inside of the UDP header. So at the application layer, DNS itself, if it doesn't get a response, you know what it's going to do? It's going to try again. So it didn't need to have the overhead at layer 4 of TCP and the three-way handshake and the synchronization and the acknowledgments. Instead, it just thought, you know what? If I don't get a response, says the king, I'll just send a request again. So there's the outbound request asking for the A record, as we looked at here. So we'd like the IP version 4 address, and the response was indeed the IP version 4 address of oracle.com that came back in. So there's our answer with that IP address. And let's see if we're going to that address. I just want to confirm that. So 23446555, and indeed we are going to that IP address. So here's what I'd like to do. I have a little homework assignment for you. I would like you to do a few commands that I'm going to demonstrate right now with you. And that is to work with and test DNS. Inside of Microsoft Windows, and there's some similar tools on Linux, and we'll take a whole chapter, another nugget in this series later on, but right now I want to share with you a tool we can use to test and verify DNS. So let's go to the command prompt. And one way of testing DNS is this. We could type in ping. Now the ping utility uses ICMP, and it sends out a packet saying hi, an echo request, and the reply comes back, hopefully, that says yes, there's reachability. We could do a ping www. Let's go to cbtnuggets.com and that's great. Well, you know, we'll start our troubleshooting section right now. So here's what's happening. The DNS is working because look what happened right here. It's telling me that it knows the IP address of that site. However, there's some filtering of ICMP, so it's not allowing the ping to actually succeed. So I'm going to do Control-C to break the sequence. And let's go to somebody that I can ping. We'll go ahead and ping www.google.com. By the way, it's not considered bad security to limit ICMP going through a firewall or a router. So here's a ping to google.com, but look at this answer here. We know just from the response that, because it also worked, that we have translation from google.com into a valid IP address. So another tool that's really cool is called Nslookup. NS standing for name server, lookup, and we could just type in, for example, www. Let's pick on Amazon. We're not picking on, we're just demonstrating. Nslookup for www.amazon.com. The first line tells us, first of all, what DNS server we're using. So this says that we're using the DNS server, Google's public DNS server. And the second line is giving us the information for it. It's saying, oh, the IP address for Amazon.com is 72.21.211.176. So that's just a really simple tool. And I'd like you to practice it. In fact, you don't need to wait. If you're on a computer right now, you can pause, right? Unless you're on an iPad, it doesn't have these same kinds of tools. But pause right now if you're on a Windows machine, and go ahead and open a command prompt and type nslookup space www.amazon.com, and it will feed you that information. Now, as we troubleshoot a network, sometimes we're sitting at a computer. Maybe we're sitting at this one right here, and we have somebody else who's complaining that DNS isn't working. So what could we do? We could have the user do this. We could say, please do an ipconfig/all and find out what their DNS server is. In this case, it's 8888. And what we could do is we could actually test the Nslookup right from our computer, but test their DNS. So for example, if we type in Nslookup and we press enter, this is the interactive mode. Look at my prompt. It's changed. It's putting me inside of this little envelope called Nslookup, and now I can do commands here. And if I want to use a different server, I could say, I want to use the server 192.168.1.1. That's an internal name resolving device I have. And once I do that, it'll say, okay, great. You want to use 192.168.1.1? I'll do it. And now we can try www.cisco.com. And now it's using the resolving server as this IP address. And then it's showing us the answer that it's getting down here. So you don't have to, you can use Nslookup to test not only your own configured DNS server for lookups, you can also use other ones. For example, if we wanted to do this, if we wanted to set the type, there's different types of records, and that's our next topic, so that's what we're getting into right now. There's different types of records with the DNS. And we've been playing so far with something called an A record. An A record equals an IPv4 address. Pretty straightforward. We also have what's called an AAA, that's Automobile Association of America, but a quad A, 4 A's, is an IPv6 address. So if we wanted to look at IPv6 information, we could go ahead. I'm going to set my DNS server back here to the original. We'll say server 8888, so I can use Google's public DNS server for these tests. And I can say set type, meaning record type, equal AAAA. So now inside of Nslookup, if I type in www.cisco.com, what I'm asking it in the background, I'm saying, hey, can you please give me the IPv6 information you have about www.cisco.com? And if we press enter, it goes out to the public DNS server, and it comes back with the responses. And here, my friends, are the beautiful IPv6 addresses that are being fed back by DNS. So I'm going to set this back to the type of A. Actually, let's do one more. Let's do MX. And then we'll do cisco.com again. And let me write out some of the more common records. Now, records just information that the DNS server has. So if we take a look at different types, we have the A record, and you know what that is. What is it? An A record is for what? You got it. It's an IP version 4 address, like dotted decimal, 4 numbers separated by 3 periods. So that's IPv4. Excellent. A quad A record, 4 A's in a row, is an IPv6 address. And that's pretty appropriate, by the way, because an IPv4 address is 32 bits long, and an IPv6 address is 128 bits as long. And that's 4 times. So a quad A record is great. There's also something called a Cname. And that is right here. So a canonical name is an alias of an existing record. So it's just another piece of information with a name associated with that IP address. And then there's MX, and MX is for mail exchange, MAIL. So if I'm an email server and I'm looking for another email server for a certain domain, so I have an email message from keith.barker@cbtnuggets.com or what have you, and my email server is trying to send it to somebody on the sprint.com network, I can do an MX record lookup for sprint.com, get that information, which is the IP address of the email server for that domain, and forward my email towards that IP address. So that's what an MX is. And then there's one other really pretty cool feature, and that's a PTR. That's a pointer record. Now, when we do normal lookups, that's when you ask DNS saying, hey, I need to find out how to get to oracle.com. That's a normal forward DNS lookup where you have a name and you want an IP address. No problem there. However, what if you have an IP address and you want to do a reverse lookup? That's what the pointer record is for inside of DNS. And it's all kept, it's all managed. So if you have an IP address and you want to find out what domain it's associated with, you can actually refer to the pointer record and have it do what's called a reverse lookup, and it'll tell you, oh, that IP address, it's managed by this domain. This last piece of dynamic DNS, it actually can mean several different things, and I'd like to talk about each of them with you. If we have a device that's being added to the network, let's say a new server, maybe this is our new web server that we're adding to our company, what we would have to do is appropriately, first of all, get a global IP address, one that's routable on the internet, not one of the RFC 1918 private addresses, but a globally routable IP address, and then have the record created for that. So if this was our company, acme.org, and this server was www, remember it's read really from right to left. So the root name servers would know where the top level domain servers are, and the top level domain servers would know where the authoritative domain servers are, and the authoritative domain servers would have an entry that says, oh, that's 24.1.2.3 for that server, www.acme.org. So anybody on the internet could find us after we had that static entry in place. So if changes occur, if we need to make changes inside our environment, there could be a period of time because of caching involved where it takes maybe up to 24 hours for updated information to clear out of everybody's cache and to accurately reflect a new number. So maybe we give this guy 2.7 instead. But the concept of dynamic DNS is when we want to have the whole DNS system updated. There's a process between service providers to do dynamic updating of DNS entries. That could be one reference to that. But another one is, let's say we bought a web camera, and we have a web camera and it's plugged in to the internet. So here's our camera. And maybe it's watching our cat or our dog or something else, or our house. And we want to be able to reach it. Now the problem with a web camera on the internet is that we're very likely assigned a dynamic IP address, maybe through DHCP. And we don't know what it's going to be all the time. So maybe 1 week we have the address of, right here, we have the address of 27.1.2.3, and 3 weeks later we have the address of 79.50.1.8. It could vary, but still we want reachability so that when we're at work or wherever is legal for you, we want to be able to connect to that camera and see what's going on. So how do you deal with that with a changing IP address? Well, that's another benefit of something called dynamic DNS. By using a dynamic DNS service, we can have software on the camera automatically report. So let's say you have a dynamic DNS server at 8.9.10.11. Just making that up. Sorry, whoever's IP address that is, sorry. So we have a dynamic DNS server and we pay them money, or they have a free service, and we train the camera, we configure it to say, hey, every time you get a new IP address, I want you to go ahead and report in to 8.9.10.11. So when the device reports in, this service, this dynamic DNS service, can make an entry inside DNS so that no matter what our IP address is, whether it changes to this or this, as the update happens in the DNS system, we can still reach it by its friendly name. Sometimes that's what they call a DNS name, is a friendly name, like www.mycamera.dynamicdns.com, a friendly name like that, as opposed to an IP address. Again, if it was just an IP address and it's changing from time to time, it's hard to keep track of. So that's the second thing. The first thing is updating DNS between service providers. The second thing could be for dynamic DNS, a camera that reports in automatically to a dynamic DNS service. And the other one could be right here at home. In Active Directory, in a Microsoft environment, Active Directory is a great way of keeping track of all the resources in a network and controlling rights and who can access what. It's fantastic. But with Active Directory, I shouldn't say but, in Active Directory, we have something called dynamic DNS. It's really not a directory function, but it's more of a feature of Windows. And so that when a PC is given an IP address via DHCP, and it could be anything on the subnet. If this is the 10.1.0.0/24 subnet, we could have any IP address between 1 and 254. So when we get an IP address, we can dynamically register that address with the Windows Dynamic DNS Server. They call it DNS. And that way the Active Directory can know exactly where we are. So I log in as Keith Barker from this machine, or the machine has a name. The machine's connected to the network. It's got a certain IP address. Now Active Directory can keep track of, not only does it know what IP address is there, it also knows the name, and it can do a friendly lookup. So we could do a lookup based on the name, and DNS could reply back to us with what the IP address is, because we registered with dynamic DNS. So what have we learned in this nugget? It's been a lot of fun. Well, we learned maybe that DNS, we're just grateful we can make a request and get an answer. So we're like looking up in a phone book, looking up somebody's name and finding out what the actual phone number is, if there's still phone books being used in the world. But DNS servers, there's 4 types. Let's talk about what they are. We have the root DNS servers, and what they know about. They're at the highest top, the peak of the top of the hill. All they really know about is the top level domain DNS servers. The TLD, top level domain DNS servers, and they know they have one for com, and one for mil, and one for org, and one for net, and so forth. So the top level domain servers, they know about the authoritative servers for various domains like Cisco, and we also have Oracle and IBM, for example. So under military, there's a whole bunch there. So for under org, we might have, let's just go to net. I know Juniper is a .net. So we have the authoritative DNS servers here, and that's 3. So root DNS, top level domain, we have the authoritative name servers, and there's one other type, and that's the type that most of us interact with. That's a resolving DNS server. That's the one who we make a request to, and it can do all the querying and legwork to figure out exactly what that IP address is. The records, the types of records include A records for IPv4, quad A records for IPv6, MX, which represents a mail, MAIL exchange record if we're looking for an email server, And we also have, what else did we miss? Oh, a canonical. CANONICAL, which is just an alias or additional names associated with that host. And then we have the PTR, which is a pointer record, and that's used for reverse lookups. When you have the name, when you have the IP address and you want to know what domain that's associated with. And those are the key ones that I want to make sure you're familiar with. Then at the very end here we had dynamic DNS, and that applies to synchronizing DNS information across the internet as it is. It could also apply to, for example, a web camera who's integrating with a dynamic DNS service, and it could also refer to dynamic updating of an IP address inside of a Windows environment. So this PC gets .58 assigned dynamically. When it connects to the domain, it can do a dynamic registration saying, oh, I just got this IP address, here's my name, and it can be inside of the DNS so that friendly lookups based on name can be resolved to IP addresses. I have absolutely had a fun time going through this process with you. We also looked at some really great tools such as Nslookup. I'd like you to practice. If nothing else, do this. Nslookup, go to a command prompt, type Nslookup space www.cbtnuggets.com just to get the feedback. And if you want to get fancier and follow me along, you can change the server and you can specify the record type, but at least go ahead and do Nslookup with at least one DNS name just so you can see it in action. I hope this has been informative for you, and I'd like to thank you for viewing.